You know, when you tap on your phone to order food, do you ever think about what's happening behind the scenes? How that single app can juggle millions of orders, update menus instantly, and almost never crash? Well, the secret isn't some giant supercomputer. It's actually a hidden revolution in how we build software. We're going to pull back that curtain and trace this incredible journey from one massive application to the super nimble, cloud-powered services we all rely on today. Not that long ago, this right here was how it was done. One big physical server, one operating system, and one single application running the whole show. Everything the app needed, logins, payments, you name it, was all bundled together into one piece. Sounds simple, right? Well, that simplicity came with some pretty major drawbacks. The biggest problem with this old way of doing things was just how inefficient it was. I mean, massively inefficient. Companies had to buy these huge, expensive servers just to handle their busiest moments, but most of the time, these machines were barely breaking a sweat. We're talking utilization often below 20%. And if you needed more power, you had to buy a whole new server, a process that could take weeks. So here's our game plan for this explainer. We're going to trace exactly how we solve these problems step by step. We'll start in the age of the monolith, then witness the first big breakthrough with the virtualization revolution. After that, we'll unpack the magic of containers and then deconstruct the application itself into what we call microservices. Finally, we'll see how these services talk to each other and what it all means for your future in the cloud. Okay, let's officially kick off our journey back in the age of the monolith. Picture this. Our application is one big, indivisible block of code running on its own dedicated physical server, what people often call bare metal. This whole model was basically a high-stakes Jenga tower. First off, you had huge upfront costs for the server itself, not to mention the constant costs for power and cooling. As we said, utilization was just awful, all that expensive hardware just sitting around. And scaling up wasn't flexible at all. You couldn't just add a little horsepower, you had to buy a whole new block. But the biggest danger? How fragile it was. A single bug in one tiny feature could bring the entire application crashing down. It was the constant fear of pulling out that one wrong block. Something had to change. And that change was virtualization. This was the first giant leap forward, and it was a brilliant solution to the wastefulness of bare metal servers. The idea was actually pretty simple. What if we could take one powerful physical server and slice it up into a bunch of smaller virtual ones? So how did they do it? Well, there's this special piece of software called a hypervisor that sits right on top of the hardware. Think of it like a traffic cop for the server's resources. It carves up the CPU, the memory, and the storage to create multiple completely isolated environments, and we call these virtual machines, or VMs. The key thing here is that each VM gets its own complete operating system, which makes it behave just like a totally separate computer. So really, the big idea here is that virtualization abstracts the hardware. It breaks that direct one-to-one link between an application and a physical machine. This is what lets one beefy server do the job of many, all at the same time. And this was an absolute game changer. Suddenly, that dismal 20% utilization shot way, way up. We could get a new server running in minutes instead of waiting days for hardware to arrive. Disaster recovery got a whole lot easier too. And of course, it saved a ton of money on hardware and electricity. For more than a decade, VMs were the gold standard. But they still weren't perfect. And that brings us to the next stop on our evolutionary journey, containers. You see, while VMs solved the hardware problem, they still had their own baggage. Each VM had to lug around a full copy of an operating system, which made them heavy and kind of slow to start up. Containers were the answer, a way to get even lighter, faster, and more portable. Just look at the difference here. Instead of that hypervisor, you have something called a container runtime. But more importantly, notice what's gone: the guest OS. Containers don't need their own operating system. They all share the underlying kernel of the main host OS, which is what makes them so incredibly small and ridiculously fast. Putting them side by side like this makes the advantage just pop. A VM gives you isolation at the operating system level, but you pay for it with all the overhead of a full OS, meaning boot times are in the minutes. A container, on the other hand, isolates at the process level and just shares the host OS. And the result? Boot times in milliseconds and barely any resource overhead. You can cram way more containers onto a single server than you ever could with VMs. Okay, so we've totally revolutionized the infrastructure, right? We went from physical servers to VMs and now to containers. But we're still running our one big monolithic application inside them. So the next logical step was to start breaking apart the application itself. And this is where we enter the era of microservices.
Now this brings us to a term that you have probably heard a million times, cloud native. It gets thrown around a lot, but it's way more than just a buzzword. It's a whole philosophy that's built around containers and microservices to squeeze every last drop of performance out of the cloud. But what does it actually mean?
At its heart, being cloud native means you're building your application as a collection of small, independent services. Those are our microservices, and you're running each one inside its own container. This whole approach is designed from the ground up for the elastic, on-demand world of the cloud. It's all about speed, agility, and the power to scale different parts of your app independently.
To really get this, let's look at our example, the food delivery app, FTGO. In its original, monolithic form, it's a mess. Everything is tangled up together in this one big hexagon. Order management, payments, notifications, delivery tracking, it's all one giant pile of code. If you want to update the payment system, you have to redeploy the entire application. It's slow, and it's incredibly risky.
So how do you untangle something like that? Well, architects follow a pretty clear three-step playbook. First, they identify all the key jobs the system does, like create order or accept order. Second, they start grouping related jobs into logical services. You get an order service, a kitchen service, and so on. And finally, they figure out how these new, separate services are going to talk to each other, which is done through APIs.
And here's the payoff. This is the after picture. It's beautiful, right? The big, tangled monolith has been broken down into this elegant suite of small, independent services. We've got an order service, a restaurant service, an accounting service, and each one has its own private data. Now, if the payment team wants to roll out an update, they can do it anytime they want without affecting anyone else. That is the agility of cloud native.
But this brings up a really important question. If all these services are now independent little islands, how do they actually talk to each other to get work done? And how can we possibly deploy updates without shutting everything down?
Well, there are two main ways they do it. The first is synchronous, which is kind of like a phone call. The order service sends a request to the payment service and then just waits for an answer. This is great for quick questions, but it means the services are tightly coupled. If the payment service is down, the order service is just stuck. The other style is asynchronous, which is more like sending a text message. The order service fires off a message and moves on. The payment service will pick it up and deal with it whenever it's ready. This is loosely coupled and way more resilient.
This loose coupling also unlocks some incredible ways to deploy new code, like this blue/green strategy. So imagine your current version, the blue fleet, is live and serving users. You can deploy the new version, the green fleet, right next to it in the exact same environment. Once you're sure the new version is working perfectly, you just flip a switch at the network level and all the traffic starts flowing to green. The result? Absolutely zero downtime for your users. And if something's wrong, you just flip the switch right back. It's amazing.
Okay, we've gone all the way from monoliths on metal to microservices in containers. This whole evolution has given us a mind-boggling array of choices for building our applications. So let's put it all together and look at that last piece of the puzzle. Where does all this stuff actually live?
At the end of the day, it mostly comes down to a choice between public and private cloud. Think of the public cloud, like AWS or Google Cloud, as renting. You're sharing a massive pool of resources with others, you pay only for what you use, and you have almost infinite room to grow. A private cloud is like owning your own house. The infrastructure is all yours, you have total control, but you also have that big initial cost, and you're responsible for all the upkeep.
And that brings us to our final question. We've just traced this incredible evolution from clunky monoliths to these complex, elegant microservice ecosystems. So does that mean the monolith is officially dead? Is it obsolete? Or is there still a time and a place for a simple, all-in-one application? Maybe the real takeaway isn't that one is always better than the other, but that the secret is choosing the right tool and the right architecture for the job at hand.